All right, guys. So we've got the file open. We've got this little dome-looking part. This is going to be a surface project, basically. We're going to take and we're going to machine vent holes in this sheet, okay, with those curves that you see there. So this is a pretty common 5-axis toolpath that you would use when you're doing stuff like this along a surface. I've seen a lot of parts from companies like Flying S that make, stuff for Tesla and things like that, and other aerospace companies where they've got very thin parts with pockets and gaps in them. And this is the type of toolpath that they're using to do that on these curvatures that they're working with. So this is a toolpath you very likely, if you end up in a 5-axis environment, that you will use a lot. So if we look at our levels here, we see that we've got our surfaces. Okay, and if I turn those on and off, that's just that sheet on top, that gray part. It's got a fixture underneath, which typically is something you would see if you're working with a really thin piece of material like you would be here. You might have a fixture that this thing's affixed down to, or in a lot of places like that, when they're working with these very thin materials, they're using vacuum tables. Okay, so a lot of their stuff that they do, the fixtures are all vacuum fixtures that suck the part down to the fixture. And then the last part you see there is the projected curves. These are the vents that have been projected down onto the surfaces that we're going to machine out of this. Okay. All right, so I'm just going to go to my top view here and kind of look down straight over the top of this. This curve toolpath, it uses the 3D curve to drive the toolpath, and then it's also going to use the vector of the surface to basically keep the tool angle where it needs to be. If you went back and you went with the exercise that this came through with, it had its rotary axis set on the x-axis, so that'd be like for a horizontal machine that had a trunnion on it. Okay, it had its rotary on the x. In our case, we're going to use the Z, so we won't have to break these up into different sections. So obviously, if this was a typical like X rotary, or like I said, a table where the Z is the X is what it's rotating around instead of the Z like ours, you may have to break this up into two halves where you'd only do this half, and then you do these parts, and then you do this half. Okay, but since we're rotating in the Z and our trunnion can kind of control everything, we can do them all at once. All right, so let's go ahead up here to multi-axis, and we're going to pick this curve toolpath, and we'll just leave the NC name just as it is. All right, everybody good? Then we're going to select library tool, and it should default to the mil_millimeter library. Just go find a flat 5mm end mill. So we're just going to get a 5mm flat end mill. Little check mark. Everybody good? Oops. Found it, but I forgot to select it. There we go. So I'll pick that. We didn't go in and set up our tool setup stuff where it would number it, so it just left it as 215. Not worried about that. Obviously, if you were running this, you'd probably want to number that accordingly or have that set up to automatically number the tools. But since we're just kind of going through the toolpath motions, we'll leave it as it is. The feed rate, let's all set that to the same thing. Let's just set that at 100 inches a minute. The plunge, let's just go to 10 inches per minute. And the spindle speed, let's just set that at 10,000. Then let's just name this. We'll call this a curve multi-axis example. And then we'll go something that's pretty common. Let's jump over to holder. We're not going to mess with this, but if I was working down in a cavity with something like this on a 5-axis machine, a multi-axis machine, I would definitely want to set up my tool holder. Okay, we're on the outside of this part, so we don't really have any kind of collision worries since we're working on the outside of this dome part. But if I was working on the inside of something where walls or whatever, any other features might come into play, and based on the way that tool's tipping, it could cause a collision. This is where I'd come in, I'd set the actual holder up and tell it the geometry of it. So there are some parts, especially if you get into like a porting situation and things like that, where you'd want to have your holder set up so it knows exactly how far over can that tool actually lean before it runs the holder even into the part. Stock, we'll just leave that as it is. Cut pattern, this is where things get creative. So we're going to use 3D curves. Okay, 3D curves are just like wireframe contours. Okay, so the direction of the chain matters. It's basically just like you see there, cutter compensation, left or right, or left or right, or you can have that set to nothing. So you see here this radial offset, that we have to tell it the radius of the tool in this. Yours should be already there, isn't it? 2.5? No? So you might put 2.5 there. But we have to go and select these curves. Alright, so let's click on these select points here. We want it to be in 3D, okay, because these are wrapped or projected to that dome feature. So they're not sitting planar, flat with the plane that we're in. So make sure you're in 3D and you want a full chain. And then these just so happen to have, they're broken at the midpoint here. You see that little point there? We don't want to select that point. We want to select the chain just to the left of the point, or to go which direction if we want to cut on the inside, counterclockwise. So I'm going to do this. I'm going to come over and set this to select only wireframe entities. That way it won't select those points because I don't want to chain those. Looks like it still will. Try not to click the point, but just click right to the left here. We'll chain that one. And then you're going to do that all the way around the part. Each one of them, you want to select it and make sure it's going counterclockwise. If you do get it the other direction, just hit the unselect and then try to reselect it the correct way. We want to get all of these going counterclockwise. You may have to rotate these up and spin the part a little bit to help you out. There we go. So I got all 9 of them selected, and I made sure I was going counterclockwise on all of them. You okay? You good? I'm talking to you. You just made like you messed something up. No, I was talking to Noah. You just oh no. Oh, you did this at the same time. I thought it was you. All right. So we'll green check mark. If I click on select points again, you should see that you've got them all selected the right way. Okay. Compensation type, notice you could set this to where, so same thing, just like we can on a 3-axis part, we could use cutter comp at the control to get these to the correct size. We'll just leave it on computer for now. Comping to the left, we selected them all the right direction, so we'll comp left to the inside of the part. Tool tip, still going to set everything off the tip of the tool. The radial offset, if the tool's 5 millimeters, we want to offset it 2.5 millimeters, so that's where that came from. And then we're going to come down here. Let's see here. The maximum step looks like it's going to basically be trajecting, or it's going to take in every 2.5 millimeters. We'll leave that set to that, but let me explain what that means. Every 2.5 millimeters, it's going to look at the surface normal again, wherever it's at on that surface. So that's basically what's going to help keep the tool perpendicular to wherever it's at traveling along the part. And between 2 points, it's going to just average itself through them. So the bigger you make that number, okay, the more gradual the transition may be as it transitions around the curve. The tighter that number is, it's going to be holding it a lot tighter. And basically what that's going to do is it's going to create more code. Okay, so if you've got a machine that has no problem processing code, and most of the time if you're on a 5-axis machine, it probably doesn't or shouldn't. You can make that number a very small increment, and that'll help just kind of keep things real tight and accurate to whatever that traveled path is. Okay, if you're having trouble and it's sitting there stuttering as it's working its way around that curve, this is somewhere you can come and open that up to try to reduce the amount of code that has to be throughput, and it could help make it run a lot smoother. But it also might give up accuracy in that case. So, all right, tool axis control. Let's go to this. At the top, you see it says lines. We are going to set that to surface for this one. And then, right here next to it, you see it says select. We're going to click that. And then I'm just going to pick these two surfaces that all of those curves are laying on. Okay, I'm picking these two top surfaces right here. Once I got those, I'll hit in selection. Output, obviously we're going to do 5-axis output. The rotary backplot, I'm going to set that to my Z-axis. That's my basically rotary. My C is going to be rotating around the Z-axis. And then I'm going to turn the angle increment on, and typically I always run this at 3 degrees. Okay. 3 degrees seems like a very, well, to be honest with you, it's the number that whenever I went through the exercises when I was a student, that's the number that they gave us, and that's the number I've always used. And I believe it's even the one that they've got using in here. It's kind of like the start number. Same thing, you can tell what it does. It just kind of opens up as it's working around. Okay, it helps open up that vector angle as you work around the curve. The vector length, okay, right now it's set to 25 millimeters. Everything's in metric right now. So basically that's 1 inch. 25.4 would be 1 inch, but and typically I leave my vector length when I'm programming in Imperial set to 1 inch anyhow. So it's pretty much right the same as what it would be if I was working in inches. Limits, if you had any axis limits that you need to set up, basically if you know that you can only rotate so far, okay, and it's got to hold itself back from these limits, you can come in here. We're going to leave them off for now. And our machine with our vector post, it pretty much knows that it needs to reorient the part. Whenever it does get to the limit on one side of the part, it'll spin the part and rotate at the same time to help create to where there really isn't, unless you get to an undercut situation, there isn't really any limits that we're going to run into. Okay, collision control. Right now it's set to on projective curve. Okay, so right now the tooltip is set to be at the depth of the curve. And you can do that if you're wanting to actually follow the curve itself, but we want to cut through this part. So what we can do is right here on the vector depth, we can tell it that we want to go another 3 millimeters deep, and you see in the graphic there what happens, it just moved it down 3 millimeters. Okay, so that's basically like setting your depth parameter in your linking parameters. Okay. Check surfaces, same thing if we had anything we're trying to avoid. This particular part, there's nothing like that, but if there was, it's the same principle as all the other toolpaths that have check or avoidance surfaces. We'll leave the infinite look ahead on, and then let's go over to our linking parameters. Okay, so these pretty much are standard as what you're used to. So right now it's in metric. Just think about that. That's not 100 inches, it's 100 millimeters. So I'm going to set that to 2 inches. So I'm going to take 2 times 25.4, so 50.8. I'm going to set my retract to 1/2 inch, so 0.5 times 25.4, 12.7. And then my feed plane, I want to feed from about 100 thou above, so I'm going to take 0.1 times 25.4, and it's going to be 2.54 for my feed plane. If you hit the drop down by linking right here, and we're going to do that, you see something that's familiar, entry exit. Let's turn those on and set those to 10 and 10. Let's do 10%, 10%. Then I'm going to carry that over to the exit as well. We're not going to do any roughing, but you can see that's there as well if you needed to rough this part. So if you need to take depth cuts to get down to your depth, if you need to do multi-passes for the walls to step over and then to a finish pass, you can use these here and it'll do that. We're just going to break through and basically drop these holes out. Okay. Planes, if you look at that, it's going to be all top. So the other day we were working with the positional 5-axis stuff where we were switching the planes up. In the multi-axis stuff, typically it's always going to be set to whatever your work coordinate system is. Okay, it's going to the multi-axis toolpath does the rotations for you. Okay, and however you drive it, it does that as well. So we're going to learn more about these different control parameters here. We're going to learn more about these as we go, and that'll kind of make more sense about what I mean by the toolpath controls, how the tooltip does. All right, so if you check mark out, it should generate a toolpath for you. If I shut my shading off, I can kind of see what it's doing. Now, I would typically, on multi-axis stuff, a lot of times, I just watch it in backplot. So I usually just go to my backplot, and that way I can see what this thing's doing here. As it rotates around the part, you can see the tools rotating around. Now if I actually wanted to see what the machine simulation would be like, I can go here and tell it to simulate the rotary axis. And then watch this. And then it shows the rotary actually rotating the part as the tool's coming straight in at whatever vector angle it's telling it to. Okay. All right. So that's basically a curved toolpath using, like I said, it's using the normals off the surface here for that toolpath. So if, for instance, I did the toolpath, and then I looked at it, and it was doing this. Okay, and I'm going, what the heck? I picked those to go to the top, and it's all flipped upside down. It's a real easy fix. Basically, it's in the actual surface itself because that's what I'm driving off of. I just went in and made the normals the opposite side. If you run into that and the toolpath's going the wrong direction, don't freak out. It's just literally the normals of the surfaces need to be flip back up the other direction. Okay, and that normal pointing up is what's going to tell the toolpath which direction to come from. All right, so that's one of the things about using a surface to drive a toolpath. Sometimes those normals can be flipped the wrong direction on the surface itself, making it think that the opposite side of the surface is the positive side, and that's the side it tries to drive from. Any questions about anything they saw in there? It's a pretty simple toolpath, and it's, you know, a lot of little stuff like this that you have to do on odd features. That's where you come in with that. Okay. All right. So in your folder, you've got a example 1 and example 2. I want you to get those done and have those ready to put in a folder for me next time. So you can probably do them real quick right now and have them done and ready. And I'll I'll have everybody put them into a folder for me on Tuesday. Okay, we'll probably, that didn't take very long, so Tuesday I'll probably look at the next 2 lessons and see, and we'll probably try to do 2 lessons on Tuesday. Okay. All right.